We've all been there. You open a complex web page, maybe a massive spreadsheet or a social media feed, and your browser should just freeze. It shouldn't respond. After all, JavaScript, the language powering most of the internet, is famously single-threaded. This means it can only do one thing at a time. So why isn't your entire internet experience a frustrating series of frozen tabs? The shocking truth is, your browser doesn't freeze because of a brilliant, invisible conductor working behind the scenes, the JavaScript event loop. Without it, every click, every network request, every animation would grind your application to a halt. Imagine trying to talk on the phone, cook dinner, and watch TV, all by yourself, at the exact same moment. You simply can't. But your browser feels like it's doing multiple things at once. It's downloading images, processing user input, and running complex animations, all without missing a beat. This crucial capability, often misunderstood, is what separates a snappy, enjoyable web experience from a completely unusable one. Let's break down this powerful mechanism, invented way back in the early 90s, that allows JavaScript to perform its multitasking magic. At the heart of JavaScript's execution is the call stack. Think of it like a single-lane highway. Only one car, or one function, can be on this highway at any given time. When you call a function, it's added to the top of this stack. When that function finishes its work, it's removed. It's a simple, straightforward last-in, first-out system. For example, if function A calls function B, and B calls C, the stack will look like C on top, then B, then A as C executes first, then B, then A. If any function takes too long on this single lane, the entire highway blocks. Your browser becomes unresponsive, you get that dreaded page not responding error. This is the synchronous nature of JavaScript in action. Most JavaScript code runs this way. When a task hits the call stack, it executes fully before anything else can happen. But we interact with web pages that need to fetch data, respond to clicks, or animate elements, all of which could take an unknown amount of time. How does our single-threaded highway handle these potential roadblocks? We need a way to offload the heavy lifting. Here's where the browser environment steps in, providing crucial tools we call web APIs. These are not part of JavaScript itself, but they're functions that your browser provides. Imagine these web APIs as a set of helpful assistants or specialized kitchen appliances. When the call stack encounters a task that might take a while, like setting a timer, fetching data from a server, or waiting for a mouse click, it doesn't block. Instead, JavaScript hands off these asynchronous tasks to the appropriate web API. For instance, setTimeout gets handed to the browser's timer API. A fetch request goes to the network API. A click listener is registered with the DOM API. The crucial point is that once the task is handed off, the call stack is immediately free to continue executing the next piece of JavaScript code. It doesn't wait around. The web API then works in the background, independently of the call stack. It's like putting a dish in the oven, the chef doesn't stand there watching it bake. They move on to the next order. When the background task, the timer expiring, the network request completing, the user clicking, finishes, the web API doesn't put it back on the call stack directly. It places its result, a callback function, into a special waiting area. Once a web API task completes its work, it doesn't immediately interrupt the call stack. That would defeat the purpose of offloading. Instead, the associated callback function, the piece of code that should run after the async task is done, is placed into what's called the callback queue. Sometimes referred to as the message queue or task queue. Think of the callback queue as a waiting room or a queue at a theme park. Tasks that have finished their background processing are lined up here, patiently waiting for their turn to get back onto the main call stack. Just like people in a queue, they enter in the order they finish and are processed in a first-in, first-out manner. This queue ensures order. No matter how many setTimeout calls or network requests finish at roughly the same time, their corresponding callbacks will enter the queue and await their turn. But who decides when a callback gets to leave the waiting room and step onto the call stack? This is where our primary orchestrator, the event loop, comes into play. The event loop is the true hero of non-blocking JavaScript. It's a perpetually running process, a vigilant manager constantly monitoring two things: is the call stack empty, and is there anything in the callback queue? This check happens in an extremely fast, continuous cycle, hundreds of times per second. Here's the dance. First, the event loop waits for the call stack to be completely empty. This means all synchronous JavaScript code has finished executing. Only then, and not a moment before, will it look at the callback queue. If the call stack is clear and there are callbacks waiting in the queue, the event loop takes the very first callback from the front of the callback queue and pushes it onto the call stack. Once on the call stack, that callback function executes just like any other piece of JavaScript. When it finishes, it's popped off the stack, and the event loop repeats its check. This cycle ensures that JavaScript remains single-threaded but can still handle long-running, asynchronous operations without freezing the entire browser. It's the constant checking and moving that keeps your web pages alive and responsive. Now, there's a subtle but crucial detail: not all callbacks are created equal. We've talked about the callback queue, which is technically the Macrotask queue. But JavaScript also has a Microtask queue. Think of it as a VIP line. Microtasks are callbacks from things like promises, specifically the .then, .catch, and .finally methods. The browser also provides queue_microtask for explicit microtask scheduling. When the call stack becomes empty, the event loop doesn't just check the Macrotask queue. First, it drains the entire Microtask queue. All pending microtasks get executed, one after another, before any macrotask from the Macrotask queue gets a chance. This means if you have a set timeout callback and a promise.then callback that are both ready to execute, the promise callback will always run first. This priority system is critical for consistent behavior, especially when dealing with modern asynchronous patterns like promises and async/await. Do you see how understanding this hierarchy changes how you reason about task execution? Set timeout equals console.log macrotask timeout 1. 0. Promise.resolve.then equals console.log microtask promise resolved 1. Set timeout equals console.log macrotask timeout 2. 0. Promise.resolve.then equals console.log microtask promise resolved 2. Console.log synchronous end. // expected output. // synchronous start. // synchronous end. // microtask promise resolved 1. // microtask promise resolved 2. // macrotask timeout 1. // macrotask timeout 2. Let's see this in action with a simple code snippet. We have synchronous console.log statements, a couple of set timeout calls set to 0 milliseconds, and a couple of promise.resolve.then calls. The set timeout 0 part is notoriously misunderstood. It doesn't mean run immediately. It means run as soon as possible after the current execution context and after all microtasks. When this script runs, synchronous start and synchronous end hit the call stack and execute instantly. Next, the call stack is empty. The event loop then checks the microtask queue. It finds and runs promise resolved 1 then promise resolved 2. Only after the entire microtask queue is empty does the event loop check the macrotask queue. It finds timeout 1 and timeout 2 and pushes them onto the call stack, one by one. The order matters: synchronous code first, then all microtasks, then macrotasks. This precise orchestration ensures that even intensive operations don't lock up your user interface. It's how web applications maintain their responsiveness, allowing you to scroll, click, and interact seamlessly while complex background tasks are processed. So, we've unraveled the JavaScript event loop, the invisible force preventing your web apps from freezing. It's the intelligent choreographer making a single-threaded language feel like a multitasking powerhouse. We covered the single-lane call stack, the background assistance of web APIs, the waiting room of the callback queue, and the vigilant event loop constantly orchestrating the show. You also now know the critical difference between microtasks and macrotasks, a priority system that dictates how asynchronous code gets its turn. Understanding this isn't just theoretical, it's fundamental to writing efficient, non-blocking JavaScript. It's how you build responsive, user-friendly applications that don't leave users staring at frozen screens. By leveraging the event loop, you ensure your applications are always perceived as fast and fluid. Next time you scroll a social media feed while new posts load, you'll know exactly what's happening behind the scenes. If you want to dive even deeper into true multitasking in JavaScript and really push the boundaries, be sure to check out our next episode where we explore web workers for parallel execution. Hit that subscribe button so you don't miss it.